We've defined a reference state for pure systems as the pure system at 1 bar of pressure, but mostly we are not working with pure systems. If we're doing chemistry, we are invariably mixing two things together, and so it will be useful to have a reference state for solutions. Let's look at what that is for a liquid-liquid solution. Recall that we have defined the standard state as the pure substance at 1 bar of pressure. And so if I have a pure solvent, it will be at the standard state. Let's now imagine adding a solute to my solvent molecules. Because the solvent is in excess, most of the interactions are still solvent-solvent interactions, although there are some solute-solvent interactions. The majority of the interactions are solvent-solvent interactions, and so the properties of the solvent change continuously as I add the solute. Therefore, it is reasonable to use the pure solvent as the standard state for my solvent in my mixture. But what about the solute molecules? If both of my mixture components are liquids and they're miscible, I can start with pure A and add red B molecules to that until I get to a 50-50 mixture. Or I can start with pure B and add A molecules until I get to a 50-50 mixture. Since our general definition of a solvent is the molecule that's in excess, and the solute is that molecule which has the least amount in the mixture, it's difficult to decide which is the solvent and which is the solute in our 50-50 mixture. For any mixtures between 50-50 and pure B, I would assign B as the solvent and A as the solute. However, for any mixtures between pure A and the 50-50 mixture, I would assign pure A as the solvent and B as the solute. In either case, the properties of the molecules in the solution change continuously as I make those solutions. And so it seems reasonable, again, to assign the standard state or a reference state for a liquid-liquid solution as the pure substance at 1 bar. With this definition, the chemical potential of pure A can be designated as mu sub A with a superscript filled in circle. Likewise, the chemical potential of pure B is mu sub B with a filled in circle superscript. The chemical potential of A in the mixture is then the chemical potential of A is equal to the chemical potential of pure A, our reference state, plus a correction for not being pure. Likewise, in the mixture, the chemical potential of component B is the chemical potential of pure B, our reference state, plus a correction for not being pure. This correction term for not being a standard state is a function of the composition of the system.